I'll now be going through a quick introduction to timsort. Timsort is a hybrid sorting algorithm and is designed to perform well on many kinds of real-world data. It's derived from merge sort and binary insertion sort. It's actually an adaptive algorithm that handles input data differently based on various factors, such as the size of the input. The adaptive sort portion has three main subroutines. The first is when there's a small size input, a simple binary linear search is used and binary insertion sort is used to sort the data. This is to reduce overhead that would arise when using any fancy algorithms. Natural runs in the data are also identified, as is the case in many real-world data, as they tend to be partially sorted. The natural runs are identified, and if they are of insufficient size, they are boosted to sufficient size via binary insertion sort. And natural runs are basically portions of the unsorted set that are actually already sorted. Natural runs that have been identified and boosted to sufficient size are then merged using one pair at a time mode by default, where one element from each natural run is compared and there's a tiebreaker, and the winner goes into the final run first. So if a particular natural run wins the tiebreaker more often than a threshold, it switches from one pair at a time mode to galloping mode, where a binary linear search is instead employed to identify the first element in the losing natural run, where the winning natural run loses out, and then the entire chunk is copied in one go. Here's a basic visualization of how timsort would work on an example array as shown here. Since it's clearly less than 64 elements long, the example can be simplified. The example will be sorted using binary insertion sort by timsort. So we have in green the list that has to be sorted, and in black the list that's already been sorted. Since 10 is the first element, it can be considered to be sorted on its own. Next we have 7, and it's inserted into the array. Now we need to do a binary search to determine the location where 7 is to be inserted. The implementation for the binary search is actually quite standard. We have the implementation of the actual binary search here, and the implementation for inserting the element, which is in a sense actually swapping the indices, which is shown here. So we have a binary insertion sort, and a search tells us that 7 is working for 10, and that is exactly what is to be done. So next we have a new element 2. So we now have a left in this, right in this, and a middle in this. So we know that the element 2 is smaller than the element at array index m, which is in the middle. So we move the index m to the left. Then we compare the element again with the array index m, which has been moved to the left. And again we see that the element is smaller. Thus we know that 2 has to appear all the way on the left. In the interest of time, I will not be going through every single iteration, so this is repeated over and over again via the binary insertion sort algorithm until the entire list has been sorted. So we'll move all the way to the end. So now we'll move on to the stability of the binary insertion sort. A sort is said to be stable if after the sort, 2 elements that compare as equal appear in the same order afterwards as they did before. The stability of binary insertion sort actually depends on its implementation, and we took care to make sure that it would be stable while we were coding it. So the stability of the binary insertion sort, as already said, depends on the implementation, and it's in our case is stable as when 2 distinct elements that are compared as if equal by the binary insertion sort. The relative order from the original unsorted list is preserved. Now for the stability of timsort, since binary insertion sort is only employed when absolutely necessary, the stability of timsort actually depends on the implementation of the merging algorithm. Care is taken in most implementations to ensure that this algorithm is stable. So, for example, when 3 runs are being considered for merging patterns such that A is smaller than B plus C, and C is smaller than or equal to B, the smaller of A and C is merged with B, and the new run then replaces the A, B, or B, C entries, which would then preserve the order of the distinct elements that compare as if equal. Now for the time complexity of binary insertion sort in timsort, the worst case for binary insertion is n squared, worst case for timsort is n log n. The reason why in the binary insertion sort the worst case is as bad as n squared is because in every ith iteration of the outer loop, the binary Search considers and repositions 0 to I, thus the worst case time complexity simply gets squared. For timsort, intuitively, since the binary insertion sort is only employed when it's not harmful to the performance as dictated by the adaptive portion of the code, the worst case for timsort would be analogous to that of merge sort, which is basically m log n. So that brings me to the end. Thank you.